Now the next two lessons, this lesson and the next lesson, address what happens if your cash flow changes over time. And that change isn't associated with interest rates or inflation. It changes because of other reasons. Well, if you know a set rate of a change, then you can deal with something we call a gradient. In this particular lesson, we're going to talk about arithmetic gradients. Arithmetic gradients deal with a set amount of change each year. So $10 today, $10 tomorrow, $10 next week, a set amount of change. For example, you're at a Ford location, or you're planning for a Ford location, and you want to install an oil water separator, and there's periodic service, and it's going to be based upon how much gallonage you have to pump out of this thing. Every once in a while, an oil water separator has to be pumped out to get all the sludge and everything out of there. And so you know there's going to be $4 a gallon that you're going to have to pump out. Last year's use was 10,000 gallons. Now we're at a site where we expect to see it expand over time, and we know that there's going to be more people coming in, and there's a certain amount of usage that this thing's going to get, and it's going to be 500 additional gallons each year. What's the net present value of that oil water separator service? And that would help you analyze maybe the different types of oil water separators, maybe the different types of services, whatever you might want to be doing as far as this analysis. So we're looking at the third of those four different equations, the arithmetic gradient equation, where there's a set increase, and again, we're going to use these set interest rates. Now the equation is even more complex, but it's got the same variables. I need to know the interest rate for the entire term of analysis. I need to know the set amount of increase. I need to know the number of years and the initial annual cost. Now this particular type of gradient breaks things up into two equations. You'll notice that the annual equation, the first thing we're doing is modeling this little bar right across here. The annual equation is the same way that we just saw it in the previous lesson. It's the same equation. So we need to first do that. The second part is we're going to model this little triangle, which is the set linear increase that we're going to have in the project. Now here's something that often confuses people, is when you're looking at these gradients, one of the things you realize is that the first cost that is incurred, the increased cost, doesn't occur until the second year. For example, this oil water separator thing. The first year is going to be $10,000, but we expect every year thereafter, the second year, third year, fourth year, an additional 500 gallons. So that might cause somebody to be inclined to try to make that end value something less than the term of analysis. Don't do that. This equation is already built for you to deal with it based upon the full term of analysis. So make sure you use the full n, not n minus 1. The other thing to watch out for is that all you need is the interest rate in the n, and this IN. I've had folks ask me, what does n stand for? It's interest rate times the number of years, okay? But it's this very similar type of equation that you might see over here. It's just got another complexity added to it. Now, let's give you an example. You've got an elevator service contract, and a service contract is the classic example of an arithmetic gradient because normally they are built when you have multiple option years for a set increase each of those option years. The first year's cost is $500, and there's a pre-negotiated increase of $25 every year thereafter. So you have 5 years that you're planning to have this contract. 5 years gives you an interest rate of 0.6%. So you can go back and see where that came from out of our little table, but for a 5-year rate, we're looking 0.6%. So we take the 25 times that gradient portion of the equation. Never forget that there's two portions to this. I'm going to do 1 plus I to the n, that's that 5-year value, minus I times n, 0.006 times 5, minus 1. And then on the bottom, I'm going to use the interest rate squared times 1 plus I to the n. And then below that, I've got the annual formula. And remember, the annual formula we already saw in the previous lesson, 1 plus I to the n minus 1 over I times 1 plus I to the n. So we multiply that out, and we'll find that the 25 times 9 that value will come out to be 9.7637, and that $500 is going to be multiplied times 4.19 or 4.91 and some odd change thereafter. Add those guys together, and it ends up being $2,699.72. Okay? Let's look at a second example. Again, you're basing, and I'm using an operational example here because I'm trying to mix it up. You're basing a potential base of operations, and you're considering the fuel operations at that location. One of the options is to order this fuel in on a contract. And let's say the term of the operation is going to be 10 years. It doesn't mean that things won't last 10 years, longer than 10 years, but you know you're going to be there 10 years as far as the anticipated term of operations. So that becomes your term of analysis. The first year, the fuel is going to be $8,000, but you expect that mission to increase each year by a percentage rate, or by a set amount, not a percentage rate, a set amount, $1,000 per each year, due to expanding people. What is the fuel cost, total fuel cost, net present value of that particular option that you want to consider? Well, we draw out the cash flow diagram, so we got 10 years. And we need to throw in there the annual cost. We got that $8,000 initial annual. Now we need to throw in there the increased based upon the amount of operation that's going to increase. Note that it starts in year 2. The equation already considers this. We do not subtract a year from the n, so the n is still going to be 10, and the I is going to be 1% for the full 10-year period. So now we've got that extra $1,000 per year each year thereafter. Remember, 2 equations. We're going to use the gradient equation to deal with the triangle, and we're going to use the annual equation to deal with the same one. And again, don't forget to use the full term. So we plug those numbers in, $8,000 into the annual, 1 plus I to the n, minus 1 over I times 1 plus I to the n. And then we deal with the gradient side of the equation, $1,000 times 1 plus I to the n minus I times n times, minus 1, divided by I squared times 1 plus I to the n. Plug it in, cram it through the calculator. The calculator moans and groans, but it comes up with a value of $1,000 times 41.8, $8,000 times 9.4, and out comes $117,614,000. Okay, you can read that. I don't have to keep saying it. Again, this is for a linear increase. We will talk in the next lesson about a percentage increase. I kind of accidentally alluded to that earlier in the lesson. So we're going to look at how to deal with when you increase on a more percentile basis. But occasionally you'll run into a linear increase. And in your notes, I show you the full up spreadsheet formula again. Make sure you build your own and test it out, because I do not want you just copying that in there and expecting it automatically to work, because all you need to do is miss a parentheses and your number will be different.